Today we're going to be solving the APMO 2019 problem 2. So the problem statement is as follows. So we have m being a fixed positive integer, and then there's an infinite sequence defined as an, which is defined in the following way. So a1 is a positive integer, and for every integer n greater than or equal to 1, we have that an plus 1 equals an squared plus 2 to the power m if an was less than 2 to the power m, and is equal to an divided by 2 if an is greater than or equal to 2 to the power m. So for each m, we determine all possible values a1 such that every term in the sequence is an integer. So now since m is a positive integer, we start by the case where m equals 1. So in this case, our definition becomes the following. We have it's equal to an squared plus 2 if an is less than 2, and an divided by 2 if an is greater than or equal to 2. So now, first we notice that if every term is an integer, we cannot have any term being odd. Because if we have an odd term, let's say an odd term greater than or equal to 2, let's say 2x plus 1, then the next term in the sequence will be 2x plus 1 over 2, which is not an integer. Now, if an is odd and less than 2, which in this case is only possible to be 1, because a1 is a positive integer. So if at any point we have 1, then the next term will be 1 squared plus 2, which is 3. And then after that, again, we'll have 3 over 2. So again, we can't have an integer. So to have this, we must have that every single term in the sequence is an integer. So now moving on, we start by letting a1 be equal to 2 to the power m, 2 to the power x, for some x. So then by the definition of the sequence, we know that we'll continue dividing by 2 until we get to be less than 2 in this case. So from 2 to the power x, we'll go to 2 to the power x minus 1, and we'll keep going till 2. But after 2, since 2 is also less than or greater than or equal to 2, the next term will be 1. So now we have an odd term, and after that we'll have 3 and 3 over 2. So again, this is not an integer. So whenever a1 is the power of 2, all terms won't be an integer when m equals 1. So we already showed that for all odd values of a1, all terms won't be an integer either. And if we let a1 be equal to some odd number, let's say l times 2 to the power x, then again we'll keep dividing by 2 until we get l. Now if l is greater than 2, and we know that l is odd in this case, the next term will be l over 2, which is again not an integer. And if l was less than 2, which is only possible if l equals 1, so that's not the case, because in this case we let l be an odd, and if it's 1, then that a1 is again 2 over x, which we already considered. So thus there are no values of a1, so that every term is an integer when m equals 1. We now move on to the case when m equals 2. So in this case, the definition of the sequence will be an plus 1 equals an squared plus 2 squared, so plus 4 if an is less than 4, and it will be equal to an over 2 again if an is greater than or equal to 4. So now we start by letting a1 equal 2 to the power x, where x is greater than or equal to 1. So then we notice that what will happen in the sequence. So we start at 2 to the power x. If x is greater or equal to 2, then we'll go to 2 to the power x minus 1, and we'll continue in such a way till we get to 2. And if x was equal to 1, then we're already at 2. So now that we're at 2, the next term, since 2 is less than 4, the next term will be 2 squared plus 4, which is 8. And then after that, 8 divided by 2, 4. Then again 2, 8, 4, 2, and so on. So this is a repeating sequence from here. And thus, since all these are integers, we know that every term in the sequence will be an integer. So when n equals 2, any power of 2 works. So a1 equals 2 over x is a valid solution. So now we let a1 be an odd integer. So again, this is the same as before. If a1 is an odd, let's say a1 equals 2x plus 1. If 2x plus 1 is more than 4, the next term will be won't be an integer, because it will be 2x plus 1 divided by 2. Now if 2x plus 1 is less than 4, so if it's an odd less than 4, the only possibilities are 1 and 3. But 1 and 3, the next term in the sequence for 1 will be 1 squared plus 4, which is 5. And for 3, it will be 3 squared plus 4, which is 13. And again, now these are odds larger than 4, so next term won't be an integer anymore. So the only case we have left now is if a1 equals 2 to the power x times L, where L is an odd, where L is odd and larger than 1. So now if L, so we started 2 to the power x times L. So clearly 2 to the power x times L is larger than 4 because L is the small value of L is 3 and the small value of 2 to the power x is 2. So 3 times 2 is more than 4. So next we'll keep dividing by 2 first. So we'll get 2 to the power x minus 1 times L and so on till we get to, eventually we'll get to L. Now if L is less than 4, then L equals 3. So next term will be again 13 and then we'll have 13 over 2, so that's not an integer anymore. Now if L was larger than 4, so we start at 2 over x times L, we keep going until we get L. Now L is odd, so the next term will be L over 2, which is not an integer. So that means that for m equals 2, the only values which work are a1 equals 2 to the power x, where x is greater than or equal to 1. So we finally consider the general case when m is larger than 2. So again, if a1 or any term in the sequence is odd, the next term or the term after that won't be an integer anymore. Let's say ai is equal to 2x plus 1 for some I. Then if 2x plus 1 is larger than 2 to the power m, then the next term won't be an integer because it's going to be odd divided by 2. In other case, if it's less than 2 to the power m, then the next term will be this thing with odd squared. So an odd squared is also an odd. An odd squared plus 2 to the power m, which is even. So the result is an odd is larger than 2 to the power m, and then the next term will be an odd divided by 2, which is not integer again. So thus we cannot have any odd term appear at any point in the sequence if we want every term to be an integer. So now we let a1 be equal to 2 to the power x as before. So now what's going to happen? If x is larger than or equal to m, then we'll keep going. So we'll have 2 to the power x, then 2 to the power x minus 1, so on till 2 to the power n. That will divide by 2 for the last time, so we'll get 2 to the power m minus 1. Then the next term will be 2 to the power m minus 1 squared, so 2 to the power 2m minus 2 plus 2 to the power m, which is equal to 2 to the power m times 2 to the power m minus 2 plus 1. Now since m is larger than 2, this term is larger than or equal to 2, since the exponent is positive. So now this is of the form L times 2 to the power m, where L is odd. So now we'll come back to this case in a while. The second case is when x is less than m for this. So then we have 2 to the power x. So it's already less than m. So the next term will be 2 to the power 2x plus 2 to the power m. So now, depending on which one of the, if 2x is larger than m or if m is larger than 2x, we'll factor that out. So let's say it's 2 to the power 2x. It's going to be 1 plus 2 to the power m minus 2x. And if it's equal to 2 to the power m, if 2 to the power m is smaller, then it's going to be 2 to the power m times 1 plus 2 to the power 2x minus m. So either way, this is again of the same form. L times 2 to the power, it's either m or 2x. So let's say L times 2 over a for general case. There are also one more possibility. Let's say 2 to the power 2x was equal to m. Then we have 2 to the power 2x times 1 plus 1, which is 2 to the power 2x plus 1, or 2 to the power m plus 1. But now we have m plus 1, which is larger than m, so it's going to be the same thing over here. So again, we'll eventually end up at a term of the form L times 2 to the power a. Just let ai be equal to 2 to the power a times L, where L is odd and larger than or equal to 3. So now in this case, there's two options. If L is larger than 2 to the power m, then basically the sequence will go as follows. So we'll have, and notice that I can also be equal to 1. So 2 to the power a times L, that doesn't really matter in this case because we're at this point, so we don't use the terms before that to calculate the next term, so we're only focusing on this term. So I can be equal to 1, that doesn't really matter in this case. So we'll keep dividing by 2, so 2 to the power a minus 1 times L, so on till L. Now since L is larger than 2 over m, the next term will be L over 2, which is not an integer. So for this case, it's not possible for ai to be equal to 2 over a times L. Now if L is less than 2 over m, and if the sequence, like we start from here, right? So we keep going. If we get L again, then again we get L over 2. But the case we have to consider is if we keep going until, let's say, 2 to the power b times L is less than 2 to the power m. So instead of getting L, there exists a power b, so that 2 to the power b times L is less than 2 to the power m. So then the next term will be 2 to the power b times L squared plus 2 to the power m. So now this equals 2 to the power 2b times L squared plus 2 to the power m. So now there are two possibilities. If m is less than 2 to the power 2b, then this will be factorized as 2 to the power m times 2 to the power 2b minus m times L squared plus 1. And if 2b is less than m, then we have 2 to the power 2b times 2 to the times L squared plus 2 to the power m minus 1 minus 2b. So again, this term, the term inside the parentheses, is odd because in this case this term is even, but we're adding 1. In this case, L is odd, so we're adding a power of 2, so that's also odd. So now this term again is of the form 2 to the power. We'll write it as a over here because a is like a general variable. It's not fixed over here. 2 to the power a times L. It's of the same form. But instead the difference is that this term is now larger. Over here we had L, but over here this term has one larger because we have L squared or something, or 2 power something times L squared plus 1. So this term is getting larger. So basically this term is increasing. So now we assume that when we had L over there, so we'll let this be L1, this is L2. And we have gotten that L2 is larger than L1. So over here we assume that there is a power B, so that 2 power B times L is less than 2 power M. But now since L is getting larger, this was L1, so now L2, maybe there's going to be some other power 2 over C, so it's less than 2 over M. But again, the term in the parentheses will keep increasing. So eventually it won't be possible since M is fixed here. Eventually we'll have some Li, so that there's no power. So we'll have Li less than 2 over M, and that's the maximum. So we can't if we have 2 times Li, it will be greater than 2 over M. So now over here, then again we'll have something like this. We'll keep going until we get Li over 2. Li, where Li is less than 2 over M, or it might be greater than 2 over M. Anyways, it's going to be odd. So then the next term, as we've shown before, will be won't be an integer, and so thus know that if AI is or A1 is to our A times L, again, no, it's not possible for all terms in the sequence to be an integer. So thus the answer is that for any m larger than 2, there exists no values of A1. We show for m equals 1, there's no values either. So the only possible answer is m equals 2, and in this case, the only values which work for A1 are A1 or any power of 2 larger than or equal to 2.